my fourth lecture. So today I will talk about angle between two subspaces of a real inner product space. At least I have told you about how the two inner product relates to angle between two subspaces having a common intersection, right, of at least one dimension, or in general n-1 dimension. Now, in general, given two subspaces of the vector space usually equipped with an inner product, how can we define the angle between them? So this is the question, and we know that the notion of angles between two subspaces of the Euclidean space has been studied by many researchers since 1950s, and in statistics, for instance, the angle is used as a measure of dependency of one set of random variables on another. So if we have a set of random variables and we want to reduce the number of variables, then we want to know how good is our approximation. The same thing also in other areas, but I'm not expert in those areas, so I cannot say too much. But in control theory, in computer graphics, in robotics, even in biochemistry, the notion of angle between two subspaces pop up. Okay, so that's why my work on this has been cited by people from physics, from biochemistry, from computer scientists, many other disciplines. I will start with this result. So after several years working on the theory of n-norm spaces and n-inner product spaces, I encountered with this paper by Ristevsky and Krenzewski, who introduced a definition of angle, I say more geometrical, in the sense that in statistics they define the angle as a sequence of angles, so we get lost what it is, I mean, geometrically, alright? So, but Ristevsky and Krenzewski introduced definition of angle between two subspaces of the Euclidean space, RG, and explained its connection with the principal angles. These are usually used by the statistician and also numerical analysis. Maybe linear algebra is also as sequence, usually a sequence of angles. And then we discovered that the definition of the angle has some error, especially in the case where the dimensions of the subspaces are different. So we tried to fix that, and we were successful. So we got a correct definition, and what was surprising is that the notion of n-norms and n-inner products enter in the definition. So if you ask what's the use of n-norms and n-inner products, this is also one of the applications. The paper you can find in the library or on the internet. So let X be a real inner product space, and U and V with dimension U less than or equal to dimension V are subspaces of X. So they are both finite dimensional, and so we want to have a formula for the angle between them. Okay, so we always assume that the dimension of U is less than or equal to the dimension of V, and think of U as for example a line, and then V a plane, for example, in R3. So we don't say the angle between V and U, but U and V. So you cannot reverse this. I mean, you don't talk about angle of subspace which has dimension larger than the other. So the order is always from the one which has a smaller dimension to larger dimension. Okay. So for example, we know in these two cases between one dimensional subspace and two-dimensional subspace, we know how to compute the angle. How is that? You just compute the orthogonal projection, and then you compute the angle between the original vector and the projection. The projection, yes. And then also, I have explained this when we discussed n-inner products. We discussed the angle between two at that time n-dimensional subspaces at that time, but now we change n to p, so between two p-dimensional subspaces intersecting on a common subspace of dimension p-1. Okay, so for your for illustration, you can think of computing the angle between two planes in R3. So before we go further, I use the word usual. What does that mean? That means that in those two cases, the angles should, because we have inner product, so the angles should coincide with the notion of angle between two vectors, right? So cosine, the cosine of that angle is the inner product divided by the product of the norms. So in the case of A, yes, we do have that, and also in the other case, we also have that. Okay, so that's what I mean by usual. If we do something, then we get the value of the cosine equal to the inner product divided by product of the norms. So in those two cases, yes, our formula coincides with the usual one. So now we want to generalize this. But before that, we observe further about the formula for those two cases. For the first one, actually, you can look at this picture. If you have just a vector u, you want to compute the angle between u and, for example, a plane like this. You project it, so the plane is v. You project it u on v, you get uv. and so this orthogonal complement is u minus, I don't have to write this, right? Yeah. We are not high school students anymore, so okay. We are not physicists also, so so this vector u minus uv is oh, hang on, I don't need that. So the cosine of the angle is the ratio between the length of the projected vector and the length of the original vector. Okay. So instead of having the inner product, I compare the norms of the projected vector and the norm of the original vector. And that's also true for the second case. So this is the key idea to compute the angle between a subspace and another subspace of maybe larger dimension. You need to know the shadow or the projected. Well, of course, here you just, for example, consider a parallelogram which has a finite area of volume. Okay, and now you consider the projection of that parallelogram on the larger subspace. So the area in general must be less than or equal to the original. If the two subspaces coincide, of course the area will be the same. But in general, it will be less. Okay? So the ratio of the area of the projected parallelogram to the area of the original parallelogram is the cosine of the angle. That is the idea. But of course, then we want to have a more explicit formula. And then we want to observe properties. So, but first of all, forget the long sentence that I wrote here. Just look at this. This is our definition of the angle between the subspace U and the subspace V. So where is V here? V is in this expression. So the projection of, so the original vectors in the subspace U, call it U1 up to UP. So that will be the denominator of the cosine. So here is in general now is the volume of the p-dimensional parallel pipe generated or spanned by the projection of each vector on V. So of course V plays a role there. Okay. We have to make sure that the ratio is a number, but intuitively it should be a number between 0 and 1. It's not negative, cannot be larger than 1, but of course we have to prove that. And it is invariant under any change of basis for U and V. And that's also important for the notion of angles. You don't want to have a formula when you change the basis, you get something else. You don't want that. Okay? So here is the theorem which says that the ratio is a number in the interval 0, 1 and is independent of the choice of basis for U and V. So we know that from the formula, I should write down the formula, projection of U1 up to the projection of UP on V divided by the anom of that and the anom of U1 up to UP. Remember that in our mind the anom is the volume, okay? And remember the property of the anoms. One of them is it is invariant under permutation. Another property is if we multiply one vector by alpha, then the modulus of alpha pops out, and so on. Okay, so the projection is invariant. The projection is invariant under the change of basis for V. Whatever the basis for V, the projection will be that vector. Okay, of course the representation will be different, but the vector itself is the same. Okay, and then the ratio is invariant under any change of basis for U. If you multiply this by 2, then you get also 2 there, and then 2 cancels out. Okay, and also it's invariant. If you swap, also you don't change, and also if you replace UI by this. This doesn't change the value of the number. That is just like you have a rectangle and then you shift this vector by that amount, you get that vector, but the area of the parallelogram is still the same. Okay? Also if you replace UI by alpha UI. Now, to prove that it is less than or equal to 1 ratio, so it's not just my intuition, and we have to prove it in mathematics. Intuition is not enough, right? Mathematics is intuition plus proof. So assuming that UI up to UP is orthonormal, why we can assume that? Because we can do the elementary law operation, so that we can do Gram-Schmidt, for example. So we can assume this without any harm. So the denominator is 1. So we just look at the numerator. The numerator by Hadamard's inequality is the product of the length of each vector. But each vector is the projection of the original vector to something. So if the original vector has length 1, then the projection should be less than or equal to 1. So for just vector and a space, that fact is trivial. Okay? So the product of 1 is of course 1. So the ratio is a number between 0 and 1. Okay. So for P equals to Q, we can prove that we can see that the angle theta between U and P is given by this formula. I will show that on board soon, but I will make some comments first. So this formula looks nice. It's just like cosine for vectors. We have this. So it looks pretty much the same, except now we have the square bracket denotes matrix. So this is a matrix of P by P. I take everything, I take this square of cosine. That means that because we are actually dealing with not just vectors, but actually lines. Okay, so there are 2 of them. two angles, but we always choose the one between 0 and pi over 2. Okay, so this is our angle. But just to avoid the plus and minus, we just take this square of this. So looking at this, in one dimension, this is just inner product of u and v. This is norm u squared, and this is norm v squared. Okay. Now it is the volume. The determinant of the gram matrix is the volume of the parallel pipe to the power of 2 or square. Okay, this is the volume of the parallel pipe spanned by VI to the power of 2. Now, this is less than or equal to 1. Then we have an inequality, and that inequality is known as Kurepa generalization of the Cauchy-Schwarz inequality. And that inequality guarantees, of course, that the expression of the right hand side is less than or equal to 1. But in our approach, we do not define the angle because of that inequality. Okay? In fact, the inequality follows from the way we define the angle. How do we define the angle? Projection. And we have just proved projection divided by the original is less than or equal to 1. But that's not projection. Okay, I will show that it is the projection. So, to make for simplicity, I will just show you 2 by 2. Okay, I don't want to write too many. So let U be the span of U1 and U2, V span of V1 and V2. So I have here the determinant of U1, V1, U1, V2, U2, V1, U2, V2, square. Oh, no. Yes, square. Okay. But this one without square. U1, 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 U2, U2, U1, U2, U2, and then V1, 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 V2, V2, V1, V2, V2. Okay, so what I will do, just elementary row operations. Okay, so but I'm not going to write in detail. So I will change, for example, U1. I will change U1 by U1 divided by its norm. This is programming notation. Okay, so if I do that, maybe the new one will be U1 star. Okay. Okay, I don't need programming. Okay. So that means I multiply the first row by 1 over norm U1. Of course, I'm assuming U1 is not 0. But then we'll change the determinant. Okay, but here I will also get the same thing. 1 from the first row, 1 from the first column. Okay? Here, just from the first row, but square. So they cancel. Okay? So now I can write U1 star, V1, U1 star, V2, square, U2, V1, U2, V2, and then here U1 star, U1 star, U1 star, U2, U2, U1 star, U2, These are still the same. Okay, but why don't we do also with U2? The same thing. U2 divided by norm U2. So now here U2, second row only but square. Here second row and also second column. So I change that too. Where else? U2 star. U2 star. Okay? Here.
One more.
Okay. We can do the same with B. Okay? But before that, hang on. Oh, I'm making a mistake. We don't do that with U2. We want U2 to be, first we do U2 minus projection of U2 to U1 star, Gram-Schmidt orthogonalization, and then U2 star is U2 prime. Okay? Okay, so that will make this become 1. And if you do the same thing for V, this will become 1 also because V1 and V2 are orthonormal. Okay, and what we are left with is just the numerator. Okay, so now my cos square theta is just U1 star, V1 star, U1 star, V2 star. I don't need stars actually, but okay. Okay. Now, is this the projection? That is my aim, right? But looking at U1 star is actually, hang on. Ooh. Okay. Okay. So what is the projection of? So we stop for a while. Now what is the projection of U1 star on V? This, if V now is spanned by V1 star and V2 star, then the projection is U1 star dot V1 star V1 star plus U1 star V2 star V2 star V2 star, right? And also the same with U2. So this is what is nice having orthonormal basis. So now if we compute this, so if we compute the 2 norm, okay, maybe take the square root, then that is just this vector, okay, this vector inner product of this and itself, okay, so that will be U1 star V1 star, this is orthogonal, so this is square, and then U1 star, hang on, yeah, this square, right? And then inner product between this and that, and so on. I mean, later on you will get that that is U1 star V1 star U1 star V2 star, and then this multiplied by its transpose. This gives the first entry there, and here you get U2 star V1 star U2 star V2 star. Okay, these are just the transpose.
square up there, I think. On the cos square.
Yeah.
Not up there. Cos square. Theta,
Oh, yeah.
yeah. No, now it's equal. Yeah.
But the determinant of the transpose is the same, right?
Yeah.
So I just proved that
Cos square.
the cosine square is equivalent, is equal to the 2 norm square of the projection vectors. So this coincides with the formula that we have before as the ratio of the area of the projected parallelogram and the area of the original parallelogram. Now, you can simplify it. I just show so the denominator becomes 1, so you just have a nice simple formula like that. Okay, and move on now. So what is wrong with Wyszynski and Densovsky formula? They define the angle between u of p dimension and v of q dimension with p less than or equal to q by this formula, which looks nice, of course. But formula, having nice formula is not enough. And they prove with quotes this inequality, which they claim as generalized Cauchy inequality. However, this inequality is only true in the case where p equals to q, we just seen that, or where v1 up to vq is orthonormal. In other cases, this formula, this inequality is wrong. So the cosine, what is wrong? The left hand side can be bigger than the right hand side. In that case, cosine square greater than 1. Of course, impossible, right? Okay. How to find the counter example? Well, it's not too hard. You just choose R3 and then U one dimensional, V is just this, V1 and V2, and then if the inequality was correct, we would have that. But when we compute the left hand side, we get a half. We compute the right hand side, we get 3/8. So of course, a half is not less than or equal to 3/8. So it's wrong. Problem is, how do we fix this? Okay. So yesterday I fixed some other papers. This time I fixed Wyszynski and Densovsky paper. First of all, for that simple case where u is just one-dimensional and v is two-dimensional, we can use our idea about the ratio between the areas. So first of all, of course, we have to compute the projection. So just one-dimensional and two-dimensional projection is given by this. You don't need to orthonormalize the basis for V. You just do the linear algebra by considering that u minus uv should be orthogonal to v. So you have a system of two linear equations, and then you solve the coefficient, you get alpha and then beta given by this, and then two inner products pop up here, and that two inner product comes from Cramer's rule. From a system of linear equation, if you solve, you use Cramer's rule. You remember Cramer's rule, okay? And this is the determinant. This is exactly Cramer's rule. Determinant of the numerator is determinant by changing one column with the column from the right hand side, and the denominator is the coefficients. So you see the coefficients. I mean V1, V2, will be there. So okay. So this using the ratio, this should be the right formula. So instead of U, V1 times U, V1, we have U, V1 times U times these two inner product, and also here. So this is what Stesky and TensorFlow means. But then, of course, what is the general formula? Okay, so we have to do linear algebra here. Projection of UI on V is given by this in general, but we have to find the scalars. The scalars are given by this. From Cramer's rule, inner product on top, the an inner product on top, and norm at the bottom. Okay? And these are the indices. The indices are all from 1 to Q except K. So that's what that means. Okay? And then if we plug this, so if we compute, we need to compute this. These are the entries of the matrix that we want to compute the determinant. Okay. So if we compute this, but first we realize that computing that is the same as computing UI with the projection. Why is that? Computing this with the projection is the same as just that one. Okay, because maybe I'm wrong. This is the projection. Yeah, computing. So if you add the orthogonal, then you just adding nothing to get something. Okay. So it's like computing the inner product between U and the basis of and the projection, something on V here, right? So you get that, and so you get this determinant. You plug all this into the formula of the N norm, and then you simplify. Quite similar to that, but now there are extra expression here because of larger dimension Q. So if Q is equal to P, then we have a nice result. But when Q is larger, then we get a little bit more expressions here. So we get M tilde instead of N. And that M tilde is matrix. Matrix is here is, I think M is P by Q. This is P by Q also, but you take the transpose, so it's Q by P. So the product is P by P. Okay. So that replaces the wrong formula that is Stesky and TensorFlow wrote. So if we divide both sides by the norm of N norm of U1 up to UP taken to the power of 2, then we get this formula. Okay. So if V1 up to VQ is orthonormal, then we get the formula 5. I don't remember what formula 5. Okay, that one. Just I mentioned that the Mistakovsky and Topology formula are correct in two cases, when P is equal to Q, or when P1 up to VQ orthonormal. Okay, so yeah, I think that's my lecture today.
Thank you.
Thank you.